Today we will be discussing about operations on independent variable. Now when I say the independent variable, if x of t is a function, it is a function of time. So the time here becomes independent variable. Now the operations which can be done on independent variable, that is time, are: one is reflection, second one is shifting, and the third one is scaling. We'll discuss one by one. First, starting with reflection. Now if I have a signal x of t, the reflection of it is x of minus t. Now let me take an example. Now if I have a function like this, that is x of t with an amplitude of plus 1, here I have 1, here I have minus 1 and amplitude of minus 1. Here the x-axis is time, t. Now if I want to plot x of minus t, I want to plot this. Now I'll take y of t, I'll assign this x of minus t to some other signal x of y of t, that is y of t is equal to x of minus t. Now the reflected signal y of t is x of minus t. Now I'll go on putting the values for t. Now y of 0 is x of 0, I'm putting the value for t. Y of 1 is x of minus 1 I get, because here I have minus t. Y of 2 is x of minus 2. But my signal is restricted from minus 1 to 1, so I need not take this into consideration. Now I have taken positive values for t, I'll take some negative values. So y of minus 1 will become x of 1 and y of minus 2 will become x of 2. Now if I draw this, y of 0 will be x of 0, so whatever I have at 0 I'll get at 0. Now y of 1, this is y of 1 is what x has to offer at minus 1. What is x of minus 1? It is minus 1. So I'll be getting the waveform here, this waveform here, and y of minus 1, that is minus 1 is present here, y of minus 1 is x of 1, so that means I'll get the waveform here. So basically reflection means you're taking the mirror image of your original signal about the y-axis. Now the second operation that can be performed on independent variable t is shifting operation. Now if I take x of t as my original signal, the shifted version of it, I'll represent it as y of t. Now how do I plot y of t given x of t? Now I'll take x of t to be a rectangular waveform of amplitude 1 which swings between 0 to 2 with respect to t. Now I'll go on giving the values for t as in the previous case of reflection, and I'll get the waveform for y of t and then I'll plot it, which is the shifted version of my original signal x of t. Now if I put t is equal to 0, I would get x of 0 minus 1, that is minus 1. Y of 1 is x of 0. Y of 2 is x of 2 minus 1, that is x of 1. Y of 3 is x of 3 minus 2, x of 2. Y of 4 is x of 4 minus 1, that is x of 3. Now if you look into the waveform x of 3, I don't have a waveform at x of 3, so I better stop iterating to the positive values of t. Now if I take the negative values of t, y of minus 1 will be x of minus 1 minus 1, it is x of minus 2. And as you can see here, there is no waveform to the left of t is equal to 0, that is at minus 1 as well as minus 2, it is 0. So I shall better stop my iteration at this point. Now if I plot this, that is y of t, it is a shifted version of x of t, I would be getting at y of 0 x of minus 1. What is there at minus 1? I don't have anything at minus 1. So at y of 0 I will be getting a 0. At y of 1 I have x of 0. That means at y of 1, at this point, whatever was there at x of 0 I will be getting at this point. Y of 2 is x of 1. So I will be having 1 here. So at y of 2 I will be having amplitude of 1. Y of 3 will be x of 2. So I will be having x of 2 is what? Amplitude is 1. Then y of 4 is x at 3. What do you have? What do I have at x is t is equal to 3? Nothing. That is 0. So my waveform is shifted right by 1. That means if I have x of t minus 1, my waveform is shifted right by 1. Now similarly, if I take an example of y of t is equal to x of t plus 1. If I go on adding the value, putting the values as I have done it here, y of 0 will be x of 1 because t will be 0, y of 1 will be x of 2, y of 2 will be x of 3. See, look into the x of t waveform, x of 3, I don't have any waveform here. So I'll better stop the iteration here. Now y of minus 1 is x of minus 1 plus 1, so x of 0. Y of minus 2 is x of minus 2 plus 1, that is x of minus 1. So do I have a waveform at x of minus 1? No. So I'll stop it here. Now if I plot this, it is y of t which is equal to x of t plus 1. Previous case it was x of t minus 1. Here it is x of t plus 1. Now at y of 0, what do I have? X of 1. What is x of 1? What do you have at x of 1? The amplitude is 1. So at y of 0, the amplitude will be 1. Y of 1 amplitude is whatever is there at x of 2. What is there? You have amplitude of 1. So this is what I get. Y of 2 is x of 3. X of 3 I don't have any waveform here. So our waveform to the right of t is equal to 0 will be truncated here. To the left of t is equal to 0, y of minus 1 is x of 0. What do you have at x of 0? 1. So at minus 1 I will be getting this. Y of minus 2 is x of minus 1. Do I have any waveform at minus 1? No. So my waveform will look like this. That means, what is the bottom line of this argument? If I have a waveform x of t and if I shift it by 1, that is x of t minus 1, my waveform will get shifted right by 1. Now if I have x of t plus 1, my waveform will get shifted left by 1. In general, if you have x of t and if you have if you're doing a manipulation x of t plus m, my waveform will be shifted left by m. And if I have x of t, if I am doing x of t minus m, my waveform will be shifted right by what amount? M. Now this shifting of waveform I have taken for a continuous time signal, that is x of t. This shifting holds good for the discrete time signal as well. Discrete time signal x of n, the same procedure or the same law holds good for discrete time signal as well. The next operation which can be done on an independent variable t is scaling operation. Now I would like to explain this with an example. So let me take an example of a continuous time signal. If I take a triangular wave which extends from -1 to +1 with an amplitude of 1 at t is equal to 0. Now, scaling means you are multiplying time with some value, some integer. Say I'll take my original signal is x of t. I'll take the scaled version of it as x of 2t. Right? Now how would I plot this? By again putting the values for t. Now if I put y of 0, I would be getting x of 0 because you get 2 into 0, that is 0. Y of 1 is x of 2. Right? Do I have a waveform at x of 2? No. So I shall stop the iteration here. Now y of -1 is x of -2. Do I have a waveform at -2? No. I shall stop it here. Now since it is a continuous time function, I can take a intermediate value in between the interval -1 to 0 and 0 to 1. So let me take y of half, that is 0.5, somewhere here. So y of half is x of 1 and y of minus half is x of -1. So if I plot this now by taking all these values, so it is y of t which is equal to x of 2t. Now what happens is y of 0 is x of 0, so whatever is the amplitude at t is equal to 0 for x of t, that will hold good for y of t as well. Now y of 1 is x of 2, that means at 1 I have x of 2. What is at x of 2? 0. So at this point I have 0, and at -1 again x of -2. X of -2 is also 0, so I will be getting 0 here. Now at y of half means what? A midway between 0 to 1. So what do I have there? It is x of 1. So at y of 0 I have x of 0, and at y of half I have x of 1. That means I'll get this waveform. And similarly y of -1 at y of minus half, that is somewhere between -1 to 0, as in at the midway of -1 to 0, I get x of -1. What is at x of -1? I get a 0. So at y of 0 I have x of 0, and from there it will come down to -1. That means I got a compressed version of x of t. Right? And what is the compression factor? It is given by 2. That means here 1 got divided by 2 and -1 got divided by 2. That means we got a compressed waveform of the x of t. Now taking another example, I'll take y of t is equal to x of t by 2. Here I had scaled it by a factor 2. I am here scaling it by a factor half. Now if I put the value y of 0 is equal to x of 0, y of 1 is equal to x of half, y of 2 is equal to x of 1, y of 3 is equal to x of 3 by 2. 3 by 2 is 1.5. Do I have a waveform at 1.5? No, I'll stop it here. Y of -1 is x of minus half, y of -2 is x of -1, y of -3 is x of -3 by 2. So I don't have a waveform at -3 by 2, whereas I have a waveform till x of -1. So I better stop. This iteration is not unnecessary. I mean, it is not required. So if I plot this function now, y of t, that is equal to x of t by 2, y of 0 is x of 0, so whatever is at x of 0, I will be getting it here, 1, amplitude is 1. Now y of 1 is x of half. What is there at x of half? X of half, see, this is a ramp which goes from 1 to 0, from 0 to 1. So at half, I will be having an amplitude of half, 0.5. right? So at y of 1 I'll be having x of half. X of half is what? 0.5. So at 1 I'll be having amplitude of 0.5. At 2 I'll be having x of 1. What is there at x of 1? I have a 0. So at 2 it will be 0. So if I join this amplitude was 0.5 as I have mentioned here. If I join this, I'll get this. And if I plot the other side of t is equal to 0, that is y of minus 1 is x of minus half, and x of minus half again is what? A 0.5 value amplitude. So 0.5, that will be coming here at minus 1. At minus 2 you'll be y of minus 2 is x of minus 1. X of minus 1 is again 0. So I'll be getting a waveform like this. So what has just happened here is, if you have a function and you scale it by a integer, I mean whole number, you will get the compressed version of it, compressed version of the original signal. Wherein if you scale it by a fraction, then you get the expanded version of it, and that expansion completely depends upon what factor you take into consideration. Here if you have taken 2 into consideration, the compression will be done on this extremities, that is 1 will go to half and minus 1 will go to minus half, so there will be a compression. And here the x of t is getting divided by 2, that means the expansion will be happening, that means your time axis is getting multiplied by 2. In the previous case it was getting divided by 2, here it will get multiplied, that means 1 becomes 2 because of the multiplication, minus 1 will become minus 2. So we got the expanded version of our original signal, right? So in general, if x of t is original signal, x of at is compressed version of x of t, whereas x of t by a is the expanded version of x of t. Now the scaling operation on discrete time signal. Now there is a slight difference between scaling operation done on continuous time signal when compared to the scaling operation that we can do on discrete time signal. Now if I take an example of a discrete time signal which extends from minus 4 to 4 with x-axis being n, and the signal is represented as x of n because it is a discrete time signal when compared to the continuous time signal which is represented as x of t. Now I have these samples as the amplitude. At 0, n is equal to 0 I have 4, n is equal to 1 I have 3, n is equal to 2, n is equal to 3 I have 1, n is equal to 4 I have half. Similarly I have the same waveform which is same samples which is repeated at minus 1, minus 2, minus 3 and minus 4. Now scaling again refers to multiplication by a number. Now if I take y of n to be scaled version of x of n, that is x of 2n, and if I go on putting the values for n, y of 0 is equal to x of 0, y of 1 is equal to x of 2, y of 2 is equal to x of 4, y of 3 is equal to x of 6. Now I need not do this iteration because x of 6 I don't have any amplitude, any sample at n is equal to 6. So I'll go for the negative. Y of minus 1 is equal to x of minus 2, y of minus 2 is equal to x of minus 4, y of minus 3 is equal to x of minus 6, which is again unnecessary because I don't have any waveform or any sample at n is equal to minus 6. So my resulting sample would be, that is y of n, that is of x of 2n, will be y of 0 is x of 0, so I will be getting 4 here. Y of 1 is x of 2. What is at x of 2? It is 2. So at 1 I will be getting 2. At 2 I will be getting whatever is there at 4. So at 2 I will be getting amplitude of half. Similarly on the left hand side, y of 3, if you want to take this, y of 3 is equal to x of 6. X of 6 is what? I don't have any waveform here, so y of 3 will be null. And y of minus 1, again it will be half. Y of minus 1 is x of minus 2. X at minus 2 is what? 2. So same amplitude as x of 1. So this will be 2, and at minus 2 I have y of minus 2 is x of minus 4. X at minus 4 is again half. So finally I got the compressed version of the original waveform. That is alright, but there is a loss of two samples on the right of n is equal to 0, that is this sample as well as this sample. Here on to the left of n is equal to 0, the sample at n is equal to minus 1 is lost, and sample at n is equal to minus 3 is lost. Why these samples are lost? Because we do not have y of y of 0.5 or y of 1.5 on n axis. That means n axis consists of only integer values, that is 0, plus or minus 1, plus or minus 2, and so on. So we'll be losing these samples when we when we scale our input signal by an integer value. That means we have lost 4 samples out of 1, 2, 3, 4, 5, 6, 7, 8, 9. That means out of 9 samples, 4 samples are lost, and we have 5 samples here. Now again, if I take an example of x of n is equal y of n is equal to x of n by 2. If I put the values, y of 0 is equal to x of 0, y of 1 is equal to x of 1 by 2, which is not valid. So I should be putting the values for which are multiples of 2. That means y of 2 will be x of 1, y of 4 will be x of 2, y of 4 is x of 4 by 2, that is 2, y of 6 is x of 3, y of 8 is x of 4, right? Then y of 10 will be x of 5. So x of 5, do I have a waveform or a sample at n is equal to 5? No. So I should be stopping my iteration at this point. Now if I go to the negative side, so if I start from y of minus 2, it will be x of minus 1. Y of minus 2 is equal to x of minus 2 by 2, it is x of minus 1. Y of minus 4 is x of minus 2. Y of minus 6 is x of minus 3. And finally, y of minus 8 is x of minus 4. That means if I plot this, y of n is equal to x of n by 2. Y of 0 is equal to x of 0. That means whatever is there at x of 0, I will be getting at y of 0 as well. So the amplitude is 4. Now y of 2 is x of 1. That means at 2 I will be getting whatever is there at x of 1. What is that? 3. Y of 4 is x of 2. X of 2, what do I have? 2. So at 4 I will be getting amplitude of 2. At 6 I will be getting the sample which is there at x of 3. What is there? It is 1. And at 8 I will be getting an amplitude of half. And same thing is repeated to the left side of n is equal to 0. That is, I will be getting 3 here at minus 2. You can check it here. Y of minus 2 is x of minus 1. X of minus 1 is 3 again. And at minus 4 I will be getting 2. At minus 6 I will be getting 1, and at minus 8 I will be getting half, as it is evident here. Y of minus 8 is x of minus 4. X of minus 4 is half. Y of minus 6 is x of minus 3, which is 1. Y of minus 4 is x of minus 2. X of minus 2 is 2. So we have got the expanded version of our original signal. That means if I have a scaling which is an integer, then my original waveform will get compressed and will lose some of the samples. Whereas if I divide n by some other factor, then my waveform will get expanded by the same factor. That is, 0 will remain at 0, 1 will be multiplied by 2, so I'll get 2 here, 2 will be multiplied by 2, that is 4, 3 will be multiplied by 2, 6, 4 will be multiplied by 2, and similarly it holds good for the negative side as well. That means this multiplying factor has a role to play when it comes to the expansion. Even it has a role to play when it comes to the compression, where in compression we lose some of the samples, but in expansion we do not lose any samples. Thank you.